The topic of this tutorial is motor starting. The two most common motor starting simulation methods are impact motor starting, which is a single snapshot when the motor first starts, and transient motor starting, which is a time-based simulation of motor acceleration. Impact motor starting simulation is used to calculate the initial voltage drop when the motor starts. It can be used to estimate the reduced motor torque, knowing that the torque drops by the square of the voltage. For example, 80% of rated voltage results in 64% of rated torque. Impact motor starting is the best option when detailed motor and load data are not available. Impact motor starting can be used to simulate the network voltage drop and motor torque under full voltage or reduced voltage starters. Impact motor starting needs essentially the same information that's required to perform a load flow simulation. You need to build a system model that includes the source impedance, cables, transformers, and loads. You need to know the motor rated size, inrush current, and starting power factor. The motor starting condition is automatically represented by a constant impedance load. When performing an impact motor starting simulation, it's important to make sure your model matches the actual pre-start operating conditions. Typically, this involves adjusting the initial source voltage so that the source bus is operating at the expected design voltage before the motor starts. Where a local generator is the primary source, the IEEE recommends representing the generator impedance with its transient value. A cable can be used to simulate series resistance and series reactance starters. A transformer can be used to simulate autotransformer, part winding, and solid-state reduced voltage starters. Looking at a graphical view of the impact motor starting model, the source is assumed to be an infinite, constant voltage, constant frequency source behind the transient short-circuit impedance. The load side of the source impedance should report 1 per unit voltage, or the expected operating voltage when the motor is offline. When the motor is switched to starting, it is represented as a constant impedance load using the motor's subtransient short-circuit impedance. The voltage drop calculated at the source and through the network impedance should provide a good approximation of the initial voltage drop that will occur when the motor starts. Transient motor starting is similar to impact motor starting, however it performs a time-based dynamic simulation involving many load flow solutions with integrated motor shaft dynamics. Transient motor starting is used to determine motor acceleration time under different load conditions, starter types, and network configurations. It reports the voltage drop everywhere in the network model during the motor acceleration and helps you determine if the motor will start. Transient motor starting is used when detailed motor and load data are available. Multiple motors can be represented dynamically in any combination, running, starting, and under load changes. Transient motor starting is an excellent tool for representing black start motor reacceleration studies. Transient motor starting calculations require the same base information as impact motor starting, including a detailed system model with source impedance, cables, transformers, and loads. In addition to the base information, motor performance data including motor torque, current, and power factor versus speed are required. Load torque versus speed and the rotational inertia of the motor and load are needed along with special starter characteristics such as capacitor assist, autotransformer, or solid-state current limit. This diagram shows the type of motor data required. It displays the motor torque, power factor, and current versus speed at rated voltage. The motor information is entered at rated voltage and is automatically adjusted as the system voltage changes. Whereas the motor torque varies with voltage, the load torque varies only with speed. This diagram shows a typical load torque profile where there is initial static breakaway torque that transitions to a dynamic torque that increases exponentially with speed. The graphical relationship of the motor speed, motor torque, motor current, and load torque is shown here. The load torque is dependent on speed. The motor torque varies with voltage, and the voltage varies with motor current and speed and other loading conditions in the network. The solution is therefore iterative and continues to increment the solution time steps until the motor torque and load torque meet at a steady-state operating condition or a stall condition. The calculation methodology for transient motor starting is to solve an initial load flow to obtain the terminal conditions for each motor at time 0. Establish the initial motor speed for all motors. Calculate the motor currents and torques using the terminal voltages from the load flow and the motor equivalent circuit or graphical model. Integrate the shaft dynamic equations to find a new speed for each motor. Calculate a new slip for each motor, then increment the time step. Perform a load flow using the new motor currents to determine a new terminal voltage condition. Continue repeating the last 5 steps until all motors achieve a steady state condition. For transient motor starting simulations, it's important to have accurate motor and load models. We also recommend validating the motor and load models with an infinite source and no network impedance. It's important to have accurate source fault impedance and to adjust the source voltage to compensate for the pre-start drop through the source impedance. Transient motor starting assumes a stiff power system where the source voltage and frequency are constant and where generator output is fixed. For dynamic simulations that include generator inertia with governor and exciter response, a transient stability simulation should be performed. Now let's step through a sample motor starting calculation. We'll begin by creating a new project. And on the one-line diagram, we'll sketch our sample system. I'll start with 3 buses. I'll connect the first 2 buses with a transformer, the second 2 buses with a cable. We'll feed the system with a utility source, and we'll add a motor that will start. Before we can start our motor, we need to define some basic system information. For this example, we'll set the utility voltage to 4,160 and the secondary voltage to 480. For the cable, we'll select from a library a low voltage, standard IEEE magnetic PVC THHN type cable. We can then select cable sizes, enter the length, and choose the number of conductors per phase. Similarly, for the transformer, we'll select from the library a typical transformer. For the utility, we need to define the available short circuit current. This can be entered in MVA, kVA, amps, or in per unit values. For this example, we'll select 300 MVA for 3-phase and 100 MVA for line to ground with an X/R of 8. For the motor component, we need to define the rated size. In this case, I'll enter 100 horsepower. For motor starting calculations, we should also enter an accurate starting power factor. Under the ANSI contribution screen, the subtransient reactance will be used to determine the inrush current. Once the system model is complete, we can run a load flow study to look at the steady state operating conditions of the system. We can look at the report format, or we can run a data block format to display results on the one-line diagram. In this case, it shows a small voltage drop at our utility bus and a 1% voltage drop at our motor bus. To evaluate the impact of the motor starting, we can select the motor and change the state from running to starting. We can then rerun the load flow study, and now it shows 5.3% voltage drop instead of 1% voltage drop. This represents the state of the system when the motor first starts, assuming a full voltage across the line starting method. If the system is fed from a standalone generator or a weak utility source, you need to pay close attention to the initial source voltage before you start the motor. For example, if we assume a weaker utility source of say 30 MVA versus 300 MVA and add additional load that may be served by the system, we can take the motor out of service and rerun our load flow. This provides us a snapshot of the system with the motor out of service, and it shows a 2% voltage drop at the utility source. It is generally assumed that the utility source is supplying rated voltage at steady state before the motor starts, and therefore we need to compensate for the voltage drop through the source impedance. Since we have a 2% voltage drop through the source impedance, I'll change the per unit driving voltage to 1.02 and rerun the load flow. It now shows 0% voltage drop at our main utility bus, which is the initial conditions we're looking for before starting this motor. We can now place the motor back in service and rerun our load flow calculation. The results now show a 2% drop at the utility bus and a 10% drop at the motor bus. These values should closely approximate the voltage drop you would see when the motor starts on this weaker system. The key here is to make sure the initial conditions are accurate when the motor is offline. If we hadn't adjusted the utility voltage, the results would have been overstated at 4% voltage drop rather than 2 at the utility bus and almost 13% voltage drop rather than 10 at the motor bus. We'll now use the same model to look at the transient motor starting simulation. Before running the transient motor starting simulation, we need to provide additional information about the motor. There's a transient motor starting subview where we can select from a library of motors. The motor library is easily customizable. To access the motor library, you can select Document, Library, PTW Library, and we'll look at the TMS or Transient Motor Starting Library. The motor model has 3 categories: single rotor, double rotor, and graphical. The single rotor is a simplified 2-path circuit model. The double rotor model is similar to the single rotor model but has an additional circuit path, resulting in a more accurate model. The most accurate representation is a graphical model where you enter points from the motor performance curves. If you don't have performance data for the motor, you can use the Typical Data button to generate a model. You can select the model type, enter the RPM, and the rated size of the motor, and a model will be created. Similarly, with the double rotor model, you can create a new motor and use the motor parameter estimation button to enter typical data to generate a more detailed model. For example, if the starting current for your motor is approximately 6 per unit, the starting torque is about 1.5 per unit, the maximum torque is 2.5 per unit, power factor at start is 0.2, and the rated power factor is 0.9, we can use the motor parameter estimator to calculate a model. The model then returns these values, which are very close to the desired values. If we'd like to experiment with weightings to improve the results of our model, we can do that as well. In addition to the motor model, we also need to define a load model. There's 2 different categories for load models, exponential and graphical. To create a new exponential load model, we can select New. We can enter the synchronous speed, torque, moment of inertia, and time constants for the equation, or use typical data, where we can enter the type of load, the rated speed, rated size, and that will return equation values where it has a breakaway torque and the torque ramps up with speed. The graphical load model is used when you have performance data from the manufacturer, where you can enter the speed and the torque and the rated torque and moment of inertia directly from the manufacturer's spec sheets. When your motor data and load data are stored in the library, you can return to the component editor for the motor, select the Transient Motor Starting subview, and use the Library button to select the motor that you've entered and the load that you've entered. In this case, I selected a typical motor and a 100 horsepower 1800 RPM fan. To run the Transient Motor Starting simulation, you can select the Run Transient Motor Starting option, and it lets you select which motors you're representing dynamically and which buses you want to see results for the voltage drop. Next, you can define the starting time for each motor. If we double-click on motor 1, the initial condition is offline, and we're going to start the motor at 1 second. Before running the motor starting simulation, you can choose the plot information you want to store. You can choose from a variety of parameters including motor speed, current, torque, and power. Bus voltage is automatically stored. Click on the Run button to bring up the TMS Study Manager, where you can define a report name and choose a time step. Click on the Run button, which will run the Transient Motor Starting simulation. Look for errors or warnings. In this case, there are no errors or warnings. When the study is complete, you can click on the Plot button to plot any of the variables from the study. In this case, we're plotting the motor speed and the bus voltage at our utility bus. It's easy to compare different operating conditions or cases in TMS. For example, the first case was starting across the line on a weak 30 MVA source. We can rename that case to represent the 30 MVA full voltage start. To compare with a 300 MVA source, we can copy the 30 MVA case, paste it in the study folder, and we can rename the new case to reflect the 300 MVA full voltage start. Before rerunning the motor starting simulation, we'll need to change the utility source from 30 MVA to 300 MVA. We'll also change the utility voltage back to 1 per unit, as there will be less voltage drop through that utility impedance. We can return to the motor starting simulation, select the 300 MVA case, run, and that generate the results to compare. In this case, we're looking at the comparison of starting on full voltage at 300 MVA source versus full voltage at a 30 MVA source. To better understand the effect that system impedance has on motor starting, we'll make a third case called No Network. We'll copy a case, paste it in the study folder, and rename the case to No Network. When we run the No Network case, we will change the study setup to ignore the network effects. In other words, it's like placing an infinite source at the motor bus to evaluate the motor performance at full design voltage. At full design voltage, it takes approximately 15 seconds for the motor to start, whereas when you include the network impedance resulting in voltage drop, it takes almost 20 seconds for the motor to start. The option to ignore the network impedance is recommended to help you validate your motor and load models. However, the exact network option should always be used for motor starting simulations. For our last comparison, we'll set up 2 new cases. Copy, paste, paste, gives us 2 new cases. We'll change the name of the first case to 300 MVA, full voltage, light load. And the second case we'll rename to 300 MVA, auto transformer, light load. Next, we'll change our system model to light load. We'll take this load 004 out of service and verify that the motor is still set to full voltage. So for this case, light load, full voltage, we run our study. And then for light load auto transformer, we'll go back to the motor and change the starter type to auto transformer. We'll use a 85% tap and remove it at 20 seconds. We can return to motor starting, select the auto transformer option, and rerun our study. For simplicity, we'll start a new plot, and we'll plot the motor speed and the bus voltage at the utility for the full voltage and the auto transformer start. Notice that the voltage drop is larger for the full voltage start, it's the blue line, compared to the auto transformer start, which is the red line. But it also takes longer to start with the auto transformer than it does full voltage. The green line is with the auto transformer, the yellow line is with the full voltage. It also points out that we've removed the auto transformer a little too early because we get a voltage drop when the starter is removed, which is almost as large as it is full voltage. TMS includes a comprehensive selection of starter types, including solid state, capacitor assist, and auto transformers. Most of the starters can be controlled by time, speed, or voltage. In addition to the graphical output, the standard motor starting report includes a detailed description of the motor and load models used in the study, an instantaneous report at the time each motor starts, and a time step report with user-defined time steps for the motor acceleration. Another useful feature in TMS is to simulate a black start reacceleration, where you may need to reaccelerate hundreds of motors as quickly as possible based on group and priority. Here you can select motors by group and assign a single starting time for the entire group. You can easily move motors between groups if voltage drop or start time limits are exceeded. The Transient Motor Starting graphical interface is extremely flexible. You can resize windows, you can change the axis ranges, you can plot in per unit or actual values, you can change the plot styles, line styles, fonts on the graph, colors on the graph, plot with and without grids, and add annotation notes. You can export the plots to a variety of file formats, and to print, simply hit the print button. This concludes the motor starting tutorial. For additional information, contact SKM Systems Analysis at www.skm.com or call 1-800-232-6789.